Hello.
Yeah, Janmajay, now it's clear. Go ahead.
All right.
All yours.
Let me start again. Let me know if the presentation is visible.
Yes, yes, it is visible.
So let's start again. Sorry about that. So yeah. So why we are concerning about deep learning right now in this era? Why in after mid of 2022 there is so much boost in deep learning? The initial paper of neural network was published in 1980s. So during that time and till 2021, I guess, there was not that much of development. It was being worked on, but people were not aware about it, mainly due to two reasons. We don't have the data availability back then that we have right now. We are living in a big data era, and we have lots of data available at our fingertips. So generally, deep learning algorithms are very data intensive. It requires lots and lots of data to be trained. And now we have that kind of a data. Second drawback of deep learning algorithm was that it requires a huge amount of computational power, which was missing. And now after the recent advancement in this GPUs, we now have that kind of a computation power to train the algorithm. So that's why we now have very various use cases of a deep learning. So there is this website called This Person Does Not Exist. It is using the DALI 2 model from the OpenAI, and it is backed by generative adversarial network. Each time you refresh it, it will generate a face of a person, which is not a real person. It's totally computer generated person, and you can try with it, and it will generate a random person each time. So it's one of the use cases for computer science, deep learning. Then there is this control of generative adversarial network that is called GAN control, in which we are keeping the identity intact and we are changing the attribute of the person. So that is one other use case which can be used in data augmentation. From NLP perspective, we are all aware of that ChatGPT and Bard. It not only can generate the text and paragraph, it can generate a code for us to review. Then there is speech to text and text to speech that comes under audio and speech processing, which help us convert our neural language to the computer understandable code and vice versa. So what is machine learning? So in previous lecture, we have seen this kind of an image that AI is a very big picture. Then we have machine learning that is a part of AI and deep learning. So we have touched some aspect of machine learning in a previous session, like a regression and logistic regression and all that. Now we are going to look at deep learning. So mainly we can divide deep learning into three parts: supervised, unsupervised, and hybrid. Supervised is a normal neural network with a little bit of twist in each variation. The multi-layer perceptron or deep neural network. Then there is a CNN, RNN. Then if you have to go ahead, there is a ResNet, VGGNet, GoogleNet, all that. Unsupervised comes under the generative AI part, in which you have generative adversarial networks, autoencoders, Gaussian mixture model, diffusion models, and all that, which generates the data uh, without any kind of a label. And hybrid is kind of a semi-supervised model of that, which uses best of both worlds. So there are some hybrid algorithms also out there. By domain perspective, we can divide deep learning into four parts. First is computer vision that deals with images and audio. Uh, the domain knowledge that required for computer vision is image processing. You should have some kind of a knowledge regarding various kind of image filters and all that. There can be a segmentation, image detection, generation and all that under this computer vision part. For text based, we have natural language processing, which translate written text into machine understandable code, and it can generate output for us. There are translation language translation task, then chatbot like ChatGPT, Bard, and all that. It comes under NLP. Each domain has their special kind of algorithm. For example, in a computer vision, we have ResNet. For NLP, we have this transformer model that's groundbreaking right now. It's the ChatGPT is a base of a GPT model, which is a derivation of a transformer model. So we have that. In speech and audio, what we do is from text to speech, speech to text, or music generation, or any kind of a task that deals with speech or audio. It comes under speech and audio. It is speech and audio module also have their own set of algorithms that is domain specific. You should have some kind of audio processing knowledge for that. MFCC and all that comes under that. Then TinyML, it concerns with edge devices, IoT devices. The constraint in TinyML we put is we don't have processing power that we have for a larger case. We don't have GPU power. So what we have to do is we have to get a maximum amount of accuracy on a minimum computational power. So there are TensorFlow version to produce a TinyML called TensorFlow Lite and TensorFlow Micro, and it deals with the hardware implementation of it. So these are the general use case and categorization of a deep learning. So we have already machine learning models right now. We have classification models, we have regression models, and it works, right? It gives you the correct output. So why go from machine learning to neural network? What is the benefit of that? So first benefit of neural network is it works really well with high dimensional large data set with complex raw data. So in a machine learning, you have a fixed up to certain dimension, it will give you a proper result. But as you go higher and higher in real life, there will be very complex data. It will not simply tabular data each and every time. So for that, machine learning algorithms kind of a lag behind the deep learning algorithm. So if you see machine learning algorithm saturates after certain amount of data, it will not give you better performance than that. But deep learning algorithms excel as the amount of data increases. So more data case where we should use the neural network instead of machine learning. Then feature extraction. So in a machine learning, we always deal with the tabular data. So if we have image or if we have text, we have to extract the feature out of it, convert it into some kind of a structured data, and then feed it to the algorithm. In a deep learning, and it will automatically feature extract and learn the patterns for that. So that is one another benefit for that. Performance improvement. As feature extraction involves human interaction with the data, and automatic feature extraction is automated. So it gives a better performance because we automatically extract a feature instead of doing a human intervention with that. So it is obvious that deep learning algorithm will give you state of the art performance in comparison to the machine learning algorithms. Generalization. So because there are deep learning algorithm has a large layers and large activation function and all that, it generalize the data and generalize the pattern and not just fit to the data. So for example, we have a training data set of dog breeds. So we provide certain kind of a dog breed to the while training the deep learning algorithm. While now during testing, we provide a dog breed that is not available in the training set. Still, based on the pattern matching and generalization, the algorithm will tell us that this is the dog, even though the machine deep learning algorithm has never seen this kind of a breed of a dog. just like a human observation, it will detect the pattern and it will successfully be able to tell you that yes, this is a dog, even though its a training part has not seen this kind of a data. So generalization is a major aspect of deep learning. Unstructured data, so we can directly provide images, text, audio, video to deep learning algorithm, and it will perform well. We can't do that in the in machine learning algorithm. So because it's able to take unstructured data, it will be much more useful in the real life scenario for that. So when you should not use the machine deep learning algorithm in compared to machine learning. So in all these slides, there is one common thing that deep learning algorithms are data incentive, which required lots and lots of data. But in certain case, you don't have that kind of a data. So in that case, machine learning algorithm will give you better output than deep learning algorithm. And another constraint is computation power. If you don't have computation power, then you should use the machine learning algorithm, which will give you better output at low computational cost. So, any doubts till now? All right.
So can you give one example of suppose we are training an image data set with a CNN or something deep learning algorithm and KNN or some machine learning algorithm and where it lacks, if you can just
So, when you are doing the deep learning algorithm, means let's say you have this image and you have to forward it to some kind of an algorithm, right? So in the CNN, what it will do is you can just take a pixel by pixel value of all the images and you can pass it to the algorithm, right? And it will extract the pattern out of that feature. For example, MNIST data set that 1, 2, 3 number kind of stuff. It will extract that pattern and it will give you the proper output with very much accuracy. For example, 97 to 98% accuracy. While in machine learning, you have to do some kind of a image processing and extract the feature out of this image first, and then you can pass that feature map to the algorithm, right? So it depends very much on how you are extracting the feature and what kind of a method you are using and what is the output of your feature extraction. So that will depend on the accuracy of the algorithm.
okay, sir.
So how the so we are now currently focusing on simple multi-layer perceptron or deep neural network and not any fancy CNN or RNA right now. So how that works? So for example, as you see in this, we have that we take a pixel by pixel value of all the images as an input. Let's say for simplicity's sake, we have two inputs. What we will do is we'll pass it to some kind of a function. This Z right now just focus that Z will provide you some kind of a probability and it will generate an output. One more thing we have here is we have a bias. So what will bias to we'll see, and the this function will give you some kind of output, which can be, for example, for binary classification, which can be true or false, or regression, which can be some kind of a value or output. Okay. Now, what this function z consists, we can divide this z into two parts. One is summation part and non-linearity. Now we will see each and every aspect of this diagram. So first of all, what is this we called bias? Okay. So bias is something kind of offset. For example, we want let's see on a chart. Okay, this is a segment function that we have seen. What it will do is, before segment, let's see, it's a line. This is a line like blue. Can you see? Hello.
Yes,
Yes.
sir.
Okay. So let's see, there is a classification task. Whatever outside of this, there are two data set for us, right? And we are dividing it based on this line. Now what we want to do is, instead of passing the line from the zero, the data set is in a certain kind that we have to offset the line in such a way that it will classify the data properly. So what we will do is, we'll give it an offset of 1 or 2, and it will properly classify the data. The thing that we did, the offset that we did, it's called bias. So no matter what value you will change of the slope, the crossing point, the intersection point will not change. So to change the intersection point, or to give an offset to your boundary condition, you have to introduce a bias to that. Same thing for sigmoid. Whatever you do with the weights, the intersection point, which is this, will not change until and unless you give the bias to it. Okay, so this is the use case of bias.
Uh,
If you have any doubts, you can just ask, right? Now, when we see the bias, now what is input? As I mentioned in earlier slide, input is what we take from the raw data. We split the raw data in, for example, this is 28 cross 28 image, and we are splitting it each pixel. So it will be 784 inputs. Input is the entry point of the neural network. You feed the data through the input layer of the neural network. It's just the entry point, nothing else. Now weights. What weights? Weights is like how much a particular input is important to the neural network. For example, you have this input called 2, you have this input called 3, and you want to do some kind of a processing in there. And all this has some kind of a weight attached to it. What this will do is, it will multiply the input with the weight. So you will have some kind of a Wx. So importance of X will be determined by the magnitude of W. What is weight? Weight is a learnable parameter. So during the training of the deep learning is to identify what value should be of the weight. What is the value of weight? Weight and bias are learnable parameters in the neural network. And initially what we do is, we take any random value for the weight, and we pass it to the neural network. And while training, with gradually updating the weight, we will learn the weight for accurate value for the output. So this is the weight in the neural network. So the weight value, this, if the weight value is 0, this connection will not work, because there is no importance of this node to the next layer. And if weight value is 1, this will be the strongly connected to the next layer. So weights vary between 0 to 1. Okay. Uh, the sum layer, what it will do is, for example, we have this 1, 2, 3 layer, and this is our sum layer. x1, x2, x3, w1, w2, w3. So what it will do is it will create x1 plus w2, x2, w3, x3. It will give the weighted sum of each and every input with respect to their weight, plus it will have some kind of a bias. Each hidden layer of the neural network will have their own bias, and the value of bias will be learned while training the neural network. So this is the use case of summation layer in the neural network. This is very simple neural network. We are just dealing with one neuron right now. The next stage will be the non-linearity of it. So why we need non-linearity? Non-linearity means some kind of a function like ReLU or sigmoid or softmax or anything. What we will do is in the summation layer we have some kind of a value wx, right? We will introduce some kind of a non-linearity to it. So why we need non-linearity? So for example, consider this kind of a data. If we are to separate it with a linear function, what it will do is it will not properly bifurcate or classify the data. So to classify this kind of non-linear data, we have to introduce some kind of a non-linearity. So in a real world, there won't be linearly separable data anywhere. It will always be non-linear. So that's why we are introducing the non-linearity here. So for in a previous session we learned about sigmoid. Then there are some more non-linear function which is called activation function that you should learn, which can be use case of that will be changed case by cases. So for example, if you want to do binary classification or multi-class classification, you can use sigmoid or softmax. Then there is ReLU. ReLU is like 0 or 1. But if you want some kind of a negative error in that, there is leaky ReLU. It's some kind of a derivation of a ReLU. So you can learn about it. Google it. It's a fairly straightforward application of the activation for you. And output. So anyone have any doubt? Am I going too fast, too slow? All right. Now this is a one layer. Now we can have a single layer can have multiple nodes. In this one, we only have one node. We can have multiple node. It's a fully connected network, so each input will contribute to each node, and there will be a weight associated with it. So if you see this 01 is zeroth input from the one first node and zeroth input to the second node. This is a notation that you should familiarize yourself with. Then we can have multiple hidden layer as well, multiple hidden layer as well. So what this sigma and this z will contain a summation part and some kind of a non-linearity part. So this there can be n number of hidden layer. It number of hidden layer changes based on the requirement or based on your experiences. You can play with it like how many hidden layer you want in your application or how many nodes in a single hidden layer you want. This is a fully connected layer. Because there are multiple layer, it's called multi-layer perceptron. And because there are multiple hidden layer, it's called deep neural network. So in a matrix formation, you can write it like that. So X transpose is nothing but a X vector in a transpose formation, and W vector contains the vector of all the weights, and then you just do matrix dot product. It will generate the same result as this one. But for the sake of simplicity, we use this matrix notation for that. So let's see how we can create a neural network. If you want, you can work with me on this, or you can just see and then do it by yourself. Let's see. For now, for simplicity's sake, I'll be using TensorFlow, but you can do the same kind of implementation is in PyTorch as well. So let's start with some basic imports.
Chanmay, zoom your screen a little bit. I mean, it's not.
Okay. Is it all right?
Yeah, now it is visible. Okay.
Okay. So these are some standard input. I don't know means I'm going to use it or not, but some standard input you should always have, so that while working you don't run out of inputs. As we are going to create a dense neural network, I'm importing dense. If you have some kind of a doubt regarding what everything is doing, TensorFlow has very nice documentation that you can follow. Okay. So in Colab, when you're working, it's advisable to create a short uh, span of code so that it will be easier to debug. Just create a short code snippet so that you can modify it when required. Okay, so it's import. Now what we want to do is we want to create a sequential model, right? A simple DNN. Now we want to add a layer, input layer. And we can have some kind of you should know what is the dimension of your input, because input layer will be the same dimension of your input. So for example, let's right now create a 2x2. Okay, this is our input layer. Then we want some kind of hidden layer, first hidden layer, which is fully connected, means dense. Let's say 1000 nodes, and activation function ReLU. You can use any activation function over here. Let's add one more hidden layer, and let's create an output layer. For multi-class classification, for example, we have 5 categories. So you should have 5 nodes for each category, each one node, and for multi-class classification, you can use softmax. And let's oh, it's not input, it's input shape. Okay. Now let's compile the model. Loss, because it's a multi-class classification, let's use categorical cross entropy loss. Now, optimizer. What is optimizer? We'll see in upcoming slides, but it's based on means my experience. If you're not sure about optimizer, just use Adam.
Okay.
And then read summary. So this is our basic fully connected neural network. We have just created it. It's as simple as this. Any doubt?
What does Adam do in optimizer part?
It's
You say that
means
you're not
oh
sure.
yeah, we'll see. We have optimize. We'll cover optimizer, some basic of optimizer, not in deep, but we'll see.
What we
And
see is SGD. We see SGD, that is stochastic gradient descent, right? So it is variant of that.
Yeah, it's one. You can use SGD over here as well. Like,
So you put SGD. So
yeah, you can use that as well.
SGD is which we just saw, right? Stochastic gradient descent. And there are more actually. So he will cover.
I have a question. So the nodes in each layer. So the first layer, for example, it has the same input and same activation function. So how is the difference? What is the difference between these nodes? 1000.
This and this. 1500. The first layer and second layer, right?
Yeah, like what is the difference between these 1000 that kind of nodes, right?
So
Janmajay was very, and for him it is very much beginning, but he didn't spend little time on the slide actually.
So let's see, we have these two inputs, right? Now for first hidden layer, that is Z1, we can have multiple nodes and everything is connected. Like, let's assume every node is connected with each other, right? We can also have a second hidden layer which can have any number of nodes. For example, right now, let's say there are now what it will do is, for example, this is x1, x2, w1, w2, and so on. So the first hidden layer, what it will do is it will introduce some kind of a linearity to the input layer, all the connected input layer, and it will give you some kind of an output probability, some between 0 to 1. Okay. Now every one of this dot in Z1 layer, you see it has some kind of a value. Any value will do, but some kind of a value, right? Now this layer will be connected to all the layers of this. Okay, and it will also have some kind of a weight attached to it. Now what it will do is, whatever the output we have in the Z1 layer, it will sum up with the weights, and it will also, in this Z2 layer, it will also use some kind of a linearity. So for what it will do is, in a visualization, if we see, let's say we have this kind of a data. So when I pass a first layer, it will have some kind of a non-linearity. It will bend the curve a little bit. Now in the second pass, we will pass this output as an input, and again introduce a non-linearity, so it will try to fit the data more accurately.
Yeah.
So by passing each hidden layer, it will learn a little bit aspect of the pattern which is there in the input.
Yes, so that's clear, Janmajay. Thanks.
Okay.
I was more of asking like the number of nodes. So Z1 layer, the first node and the second node, because their input is same, function is also same.
No, the Z1 has an input of the Z1. This layer, it's a Z1. Let's name it so that it will be easier. Okay, so this layer will have this input layer as an input. Okay, and the Z2 layer will have Z1 as an input.
Yeah, yeah.
Okay.
But the nodes in Z1, I was saying that if we,
Janmajay, I think he's asking very basic question. Can you go back to your slide? I mean, see, he may be not knowing the what layer is and what is this neuron. Just that, yeah, just above that sigmoidian, just above that, the logistic regression basically. Yeah, just click there. So this is what? This is a logistic regression, right? How it is logistic regression? When you put this, let me clear. Sorry, Janmajay. Yeah. So this is this. If you put this choose this is a sigmoid. This is our logistic regression, right? I think you should all understand. So this is a particular. We call this as a neuron, a one neuron. Okay. So what we are doing here, we are classifying in two part, right? I mean, whether it is a class or not class. If you have a three class, right? Then how will you do? We will not be able to do this. What we will do? We will create a parallel stream like this. Okay. This is another
Yusuf
sigmoid
sir,
function.
are you sharing your screen?
I think you must be seeing the same screen, right? No. I'm writing on. Also, I am writing, but it is not visible. Okay. Let me share. No, I'm not able to share. I'm writing, but yeah. So I don't have that science. So let me say this. Okay. Let me share my screen. Okay. Sorry, Janmajay, I'm disturbing your class, but let me. I'm just covering basic actually, so everybody understand what you are going to cover. So basically, this is like let's say this is input, right? This is one x1 and x2. This is a input layer. Okay. Now what we had some w0, w1 and w2, right? And this is a summation, right? And what we do, we pass it to the sigmoid function, right? And then we get our y. So this is our logistic regression, right?
Yeah.
So now see, this is called input layer. The first layer is input layer. The second, this layer, this is actually one, right? In one neuron, we write it as G actually. Okay. So this is a hidden layer, and this is our output. So this is output layer. Okay. So input, hidden layer, and output layer. So hidden layer is basically here one layer. So this is a in logistic perceptron. Now this will classify as 0 and 1. Right? Sigmoid will give what is the value of sigmoid function output of sigmoid 0 to 1, right? Range of sigmoid is. We have seen that. I mean, if you have not seen, just look at it again. So it will give output 0 to 1. So it will output the probability of a class. But if you have a 3 class, you will not be able to do it, right? So what we will do in that case, you will add You will do the same thing again here. You will choose the you'll take the summation here. You will take the another sigmoid here, and you will output another y hat 1 and y hat 2. Okay, we'll pass this 2. What we will do here, I mean, actually not 2, 3. If there are 3 class, then we will have a 3. And we will give this input to this also, basically. We will have another 3. So we will have a matrix where W0, W1, W2 of 3 rows, right? So 9 parameters, basically, here. Right now it's going only one layer, so there are 3 W's. It will go to this line also, and there are another third one also here. So it will all this go to third also, and there are different parameters, 3. So now this layer is having a 3 neurons. We can say this layer has a 3 neurons, and this output has a 3 outputs. Okay, so these 3 neurons you can specify in that count. That 1000 is this 3 actually. So we are saying we have a 3 input, make it 1000, make it 500 again, and make it 6, whatever. I mean, so you can choose your it is basically network choice which you can do. It depends on the task how you will choose. It's completely depend on task. Go ahead. I think it I cover your point, right?
Yeah.
Okay, go ahead,
Sir,
Janmajay. Yeah, go ahead. Somebody is asking. Go ahead, please. Okay, no worry. Okay. Yeah, Janmajay, go ahead. I'll stop my screen.
So, are you guys tired, or should we continue, or should we take 10 minutes break?
Continue, I think,
I
right?
guess, yeah, I guess we can continue.
Janmajay, your mic is, I think, you are muted.
sure,
So,
sir. Sorry, Janmajay.
yeah.
Yeah.
Sure, sir. So this, how many neurons that we want to add, that depends exactly like what inputs we have, right? Like X and Y.
It's your design choice, and it's completely based on intuition. And there are, I mean, you can leave how people use it, but
Mhm.
that's completely on a their task and your design choice. It's
Okay.
not something mathematically can be proven.
Okay.
So there's this, let's see, count of this parameter, count of W's, which you heard in the lot of time, right? There are a billion parameter. So that's a count of this. Here you are seeing this number of parameters. Janmajay is showing a trainable parameter. And total, I mean, all are trainable. So here, just creating a simple neural network like this, it has a 5 lakh parameter. So there are 5 lakhs weights. Okay.
Okay.
So each layer, this is the count of how many layers. See, there are 1000 neuron we take. We pass input as 4. 1 is bias. So 4 plus 1 is 5. 5 into 1000. So it is 5000. The second layer, we have a 5000 as input. We have a 500 as a, so 5001 into 500. Because one bias also we add, every layer we add one bar bias. So 5001 into 500. So it is like 5 lakh 500, right? If you sum, and last layer, the input is 500. The output of the previous layer becomes the input for the next layer, right? So that's why 500 is the input. So 501 into 5. So it will be 2505. So if you sum that, it will give you the total number.
Okay. So it doesn't depend like how many records you have in your data set.
No, it's your network choice, how you wanted to design your network. And this is your memory. This will make the parameter is the learning memory. It will remember something, right? When you train the data, then data is not being stored in the network, but the outcome of the algorithm is being stored in the parameter. So it remembers. So you need to choose how much memory I need for this particular task.
So only thing fixed is this nodes of output layer. Like what is the output that you require, that is fixed. Otherwise, you can experiment with this value. For example, I have 5 categories, so I have choose the output layer as 5. If I have like say 10 categories, so I will choose this as a 10. If
Mhm.
I want true or false, I will choose this as 1, and I will convert it to sigma. So this is fixed. Otherwise, you can just experiment with all the other. This
Okay.
the
So taking
output.
this
No.
1,500 is totally experimental, right? There is no standard
Yes.
guide for that.
Yes.
Okay.
Two things is the shape of the input and what output you desire. Otherwise, you can add one more layer over here, or you can change the node of that. Everything is based on your experience and experiment.
Okay. So next, let's say we are adding this Z1, Z2 to hidden layers, right? So how we can decide? Let's say if I like in my based on my data or based on my network choice, I need to add one more, right? That will come with the experiment. So is it there will be any comparison at the end with the output? Like we are expecting, like as you said, the 10 classes, right? And with the let's say if you compile the model and we are getting I mean, is it going to like we'll always get the 10 classes, or is it possible like sometimes we get 8 classes, sometimes we get 11 classes?
Whatever you define over here in output layer. So this is your output layer.
You have a problem, right? Your problem, you know, right? I mean, how
Yes,
many
yes,
class you have.
yes.
So I mean, whatever your task, so that based on task you decide. I mean, you wanted to segregate the something in a 12 color, then
Hmm.
12 is your output, and what is your input is also what kind of data you have available. Based on that,
Yes, sir, but
let's
what
say,
based on which factor? Let's say I have
So
decided 10 colors. Based on which factor I should decide, like I should add one more layer or I should reduce one more layer, like to
okay,
improve the accuracy of the network.
so
so yeah, go
kind
ahead.
of a give means take if you have computation power, you can
Mhm.
add one more layer, but there is a limit to that. If you add too much of a layer, it will overfit. So there are techniques to avoid overfitting. But one thing you should consider is how much computation power you had. You should make your network as deep as your computation power. And if it's overfitting, then you went too far. Means if it's overfitting, you should decrease your hidden layer and your number of nodes.
So
Two
and
things you
then it
should
will give the
consider.
precision, right? And then it will give the precision whether it's underfit, whether it's overfit, right?
Yeah, based on your training, you will get if it's overfitting or underfitting.
Okay. Okay, I think yeah, that answers my question. Thank you, sir.
Okay. So shall we continue?
Please go ahead.
So I have created this neural network. Now, if I pass some kind of input to this neural network, will it give me the correct output? No, right? Because the weights are randomly initialized and we have not trained it. So our next phase of deep learning is to train the neural network. So in training, it contains two phases. One is forward propagation and one is backward propagation. In forward propagation, what it will do is it will take the input, multiply it with the weights, add some kind of a non-linearity, again multiply that output with some kind of a weight and generate the output. So this is our forward propagation. So if I can see, first we take the input, then we multiply all the inputs with the weights, then we introduce it some kind of a non-linearity. So it will generate an output, and based on weights, some node will have more priority, more weight than compared to other. For example, Z2 has more priority than Z1. Then we multiply that with weights of the second pass, and it will generate us our output. It, for like this, it's true or false or anything. Okay. So now we have that output. For example, let's say this is our output y dash. Okay, and our real value is y. So we have to calculate the loss, like what we have predicted and what is the correct value. There has to be some kind of a difference between those. So we have to calculate loss. Now there can be many type of loss. So we are familiarized. We have worked with MSE, right? Mean squared error, and MSLE we are using in our critical computation. Then there is binary cross entropy. So two class classification. Then categorical cross entropy, multi-class classification that we have used in our that code. Then there is this KL divergence. So KL divergence, what it will do, it will give you difference between two distributions. What I mean to say is, let's say we have this one distribution predicted, and this is original. So there is some kind of a difference between these two distributions, right? That difference will be given to us by KL divergence. So if you are interested, there are many more ways to calculate the error, and you can look into it. But these are some of the most commonly used errors in deep learning. So we got our error function, and so this is our error function. What we'll do is, for all the y dash that the network has produced, we will sum, average it, sum and divide, means this will average the error, and we want to find we want to minimize the error. Our goal is to minimize the error. So this is our goal. Now, generally we are using gradient descent, and I think gradient descent is covered in a previous session. So I'll quickly go through it so that we can familiarize with ourselves. So just remember, this is our goal, to minimize the error. Okay. So what we will do is, we will randomly in this, for example, this is the distribution graph of uh, our data set, right? We will randomly pick W1 and W0 and W1, because we have the simple neural network. Just consider it as a W0 and W1. Now what we will do is, we will differentiate it. The partial differentiation with respect to weight, what it will give you is steepest ascent, like in which direction I should go, that my changes error will be maximized. But what we want to do is, we want to minimize our error, right? So it's simple, we just go in the opposite direction of the partial differentiation. Okay. With eta step, eta is a learning rate. We'll see what eta is. We'll just repeat this process until we are reaching in a minimum. So this is a simple gradient descent. I have added one link over here. So if you are not familiarized, or if you want to learn more about it, you can just use this. Okay. So we are aware of gradient descent, but we don't know how to calculate this partial differentiation of the weights. How to calculate gradient? To calculate the gradient, it's a process called backpropagation. So let's consider this simple network. So what it has one input x1, one hidden layer z, which contains a summation layer and non-linearity, and it will generate some kind of output y dash. And this is our real value y, which we want to achieve. Some kind of a function MSE or any error function. This is our error function. Okay. So our goal is to minimize error function against so this can be this will be for W2 and because remember W if you remember previously W is just a vector of weights, right? So what we want to do is we want to change the value of W2 such a way if we introduce a minor change in W2, what is happening to cost? And we want to find a minor change such a way that cost is decreased. And same way, if we do a minor change in W1, it will change the summation, which will change the output of this non-linearity, which will affect the output. So minor change in W1, what minor change in W1 that I should do, which will decrease my overall cost, and same for W2. Okay, so let's see. Our goal is to find a partial derivation of error with respect to weight W2 and with respect to weight W1. So let's this is our y dash, right? What it depends on? It depends on W2 and Z. And we want this. So I think most of you are familiarized with the chain rule of partial derivation. So what we want to do is we want to find the derivation of JW with respect to W2. So what we will do is we will find the derivation of JW with respect to the y dash and y dash derivation with respect to W2, which will give you the same result as partial derivation of JW with respect to W2. Is it clear? This is initial first layer of backpropagation. If you have any doubt, you just ask. Hello. Okay, so no doubt. Now, what we want to do is now we want to find the partial derivative of error with respect to W1. So in this case, when we are doing the W2, we have this W2, just replace this with W1 and we'll get a partial derivation with respect to W1. Now, if you see JW is dependent on the output, this will depend on W2 and Z, and Z will depend on W1 and X1. Now we want to find the partial derivative of this with respect to this. So what we will do is we will find the partial derivative of JW with respect to y dash, and then y dash with respect to Z, and Z with respect to W1. Just like the first year, this is a chain rule of partial derivation. Okay. So JW differentiation of error with respect to output will be the same. Then we will find partial differentiation of output with respect to the hidden layer Z and hidden layer Z with respect to W1, which will give us this. Now we have a direction in which W2 should change and a direction in which W1 should change, which will minimize our error. Okay. So what we will do is we will update the value of W2 such a way that current value minus learning rate and our direction. Now, what is learning rate? Learning rate is nothing but the step in the gradient descent. If you see how much should I go in the given direction, how much should I go in this direction, that is my learning rate effect. Okay, so why we are doing this, like why can't I just go full, means whatever I got by JW. So in, if you see this distribution, there are multiple maxima and multiple minima. So we want to converge our gradient descent. I think this was covered earlier, but just to recap this, what our goal is to converge our algorithm such that way it reaches the global minima. So that's why we are taking the small step in the direction. This is the implementation of stochastic gradient descent that was covered. So eta is a learning rate, and that can, means user, it's learning. User can choose whatever the learning parameter they want based on their experience. Okay, so any doubt till now?
No, sir.
So this is the basics of backpropagation. Now there can be multiple layer. So the concept will remain the same, but you just have to keep track of more indices. Like for example, if there are two hidden layers, then this will become Z1, there will be Z2 and all that, right? So I found one blog which explained this very easily in a visualization. I have added a link over here as well for this. So what it will do is it will calculate the back propagation with respect to all the node that W11 is affecting. Okay. So it's the same principle that we are using in a single neuron. If there are stack of it, you just have to sum the weights, sum the partial derivation. If you see over here, uh, for second layer, it is just doing the sum for same thing. Okay. So this is a generic formula for each weight. Z is our training epoch. For each epoch, you should update the W with the direction you get, multiply by learning rate. Anyone has any doubt in backpropagation?
No.
Chandra, just one
Yeah.
thing.
Yeah.
Are we going to separately give it these load values again? Like we have the output, input and output values, but what about the interlayer?
The W, this W value.
This Z1.
Z is nothing but a summation of x1 w1 with some kind of a non-linear function. This can be sigmoid or softmax or ReLU or anything.
Okay. So um,
So it's calculated value. We don't have to provide.
okay.
Anybody else?
So I just want to confirm the flow, whether it is the right understanding or not.
Okay.
Let us say, for example, we have few elements for making a good tea, like milk and then
Mhm.
chai patti and whatever, all those elements.
Mhm.
Now, suppose one of the element is more and taste wise it's giving error. So
Hmm.
the more element has more weight. For example, x2 is the element and w2 is more weight. So we are trying to figure it out that where is the taste bad due to this more weight, and if we truly find out that using partial derivative, then we try to decrease it. Is it the correct way of interpretation?
Yeah. For example, there is too much sugar in tea. So W is number of spoon. So you just have to decrease it, and that is learned parameter. Means when you do the training, the value of W will change, and after certain epochs, it will converge to certain value.
Okay. And we are using partial derivative to
Yes.
find that how much is relative, and after getting those values from partial derivative, we say that okay, now let us change it in reverse direction so that error minimizes.
Change it in a such a way that my error minimizes. Yeah, correct.
Yeah, okay.
So anyone has any other doubt? Ishan, sir, you want to add anything? Otherwise, we can move to implementation.
Go ahead. Go ahead.
So
I mean,
we
anybody has a question, then we can. If nobody, if if somebody wants to, is it clear? I mean, how W is changing, all parameters are changing. If anybody has doubt, ask it. This is right time because this is what is all about neural network. This is very basic and fundamental of neural network.
all
Backpropagation.
all the neural network will follow this back propagation and forward pass and all that. So you should have very clear idea about it.
Okay, go ahead, Janji. I think.
Okay. So we have this our neural network with us. Now let's get some data set. So what I'm doing is I'm getting a training data set and testing data set. You can load it via CSV or some external. But this Keras has some data set preview. So we are going to use that. We are going to use MNIST data set for. Uh, Let me show you what is MNIST. MNIST data set is like handwritten has captured handwritten digits of many example of each letter and they converted it to this grayscale. So what we are going to try now is we are going to try to identify this handwritten digit. So in TensorFlow you can just get it because it's available right out of the library. I can use it. If not, then you have to load the data via pandas data frame. Or if it's image, you have to use some kind of matrix operation to load the images. Okay. Now let's normalize the data so that all data will have the same size and dimension. We don't care about the labels right now. So let's see. what I'm doing is I'm iterating over my training data set, and I'll print random value, random images from that data set. Creating a subplot. Dot, file, two, record. Data set is loaded. So this is our training data set, right? Random images of handwritten digits, and what we are going to do. So, and this is a more famous data set, so I won't be doing any EDA. But if it's new data set for you, you should do exploratory data analysis to identify how many training sets are there, what are the dimensions, what is the data, how it's distributed. You should find out doing the data analysis. Now to do the training to forward and backward, because we are using a library model, right? Yeah, we can just do it. So you can manually write your forward pass function, backward pass function, and pass the data through it, or you can just use the library. Because in the real world, we are not going to write the function by ourselves. So I'm not going to show you, but if you are interested, there are blogs out there that you should do. That's 20 blocks. And this validation split, what will we do is it will split the training data set like 80% to train and 20% to validate, so that we have some kind of a matrix like what is the training accuracy and what is the validation accuracy. Because it's an MNIST data set, the image size is 28 plus 28. So see, the input layer is dependent on the data set. I have not kept the correct value, so that it is showing the other. Now it should work. Oh, I didn't compile. Compiled. Okay. So what it will do is it will do 15 times the forward propagation and backward propagation. For each time, it will calculate all the weights. As sir mentioned, these are the number of weights or parallel trainable parameter. It will calculate the error. It will calculate the gradient. It will update the value, and then in next pass do all over again. So right now I have kept it at 15. You can experiment with this as well. So if you are doing the epoch like 100, and if you see your training accuracy is reaching 100% and your validation accuracy is decreasing, that means you have overdone it. It's overfitting. You decrease your epoch. So while it's training, anyone has any doubt till now? If you see, my training accuracy is increasing. The same for my validation accuracy. It's also increasing.
Meanwhile, you have to fill the attendance form. Let me share it here, okay? So you will know while who were at present or not. Fill this form, okay, for today's session. I just share in the chat.
So Janmajay, I have a question. So you said if it's 100%, it's overfitting. I mean, what is wrong with
So
achieving full accuracy?
the thing is, it's not wrong if the training accuracy is 100%. The full case was if training accuracy was 100% and your validation accuracy is decreasing, means what? Your algorithm is overly fitting over your training data set and not generalized it properly. So, for example, you have this kind of a data set. So now what overfitting does is it will overly fit to this data set. So what it will do is anything here, this side of the thing, it's one category and this side of a thing is another category. Now in testing data set, it's possible that this will also be category X and here category will be Y. So the generalization, what should have happened is it should have taken this kind of an approach. This should be our ideal situation. But the overfitting, what is the it overfit the training data set. So now the testing data set accuracy will decrease. It will not generalize properly on the data. That is our issue. While explaining, if I can speaker, might find this effective. If you see, this is overfitting. It should not have happened like it should have generalized the output like this.
Yeah.
Okay, so let's stop here. We have trained the model for 10 epochs instead of 15. Let's see what is the accuracy on training data, testing data. So to train the data, we use the fit function. To evaluate the data, what will we do? We will use predict, and we will pass testing data set. And because it's a multi-class softmax we are using, it will provide us the probability. So what we want is we will want the value with the highest probability. This will give us that. Okay, it's done. Let's print. Predicted value. Okay, so let's multiply that. So even with just 10 epochs, our model is giving 98% accuracy. in compared to machine learning algorithm, the out of the box model, we didn't even optimize this layer or this epochs or anything. It is giving us a good result. So, anyone has any doubt till now? Okay, so the last part of this that I want to cover is this overfitting issue. So if you see the training accuracy is, training error is decreasing very drastically, but validation error is not decreasing. So this is the issue of overfitting. It happens on all the algorithms, even if machine learning or deep learning. So in the deep learning, there are certain ways you can prevent it. Early stopping is one of the way. For example, in this model, if I have kept it 100, after certain period of time, model will overfit on the training data set. So what you should do is, instead of keeping in 100, I kept it 15. That's early stopping. Stop before the model overfits. Then data augmentation. If you have very large data set from which model can expect a pattern, there are a lot less chances of model to be overfit on the data. So data augmentation, you can increase your data by doing the data augmentation. Regularization, there is this concept called L1, L2 regularization. We'll see if we get the time in the future session. We'll take the regularization as a part of presentation. And dropouts. What dropout? In all the models, what we have seen is every layer is a fully connected layer, right? This will connect to all. This will connect here. So dropout is just randomly on each training set. For example, on a first training set, drop couple of connection. On the second, keep that and drop some other. So in that way, uh, the data will shuffle itself because some of the connection will not be there, and it will prevent the overfitting of your model. Uh, Even still, if you have some doubts, look into it. Means there are materials out there. It will be really helpful if you understand all that. Like for now, it basic neural network, it won't matter much. But in the complex data set, you will need this kind of a technique to train the model more efficiently. And lastly, if you have trouble visualizing what we have done today, I would suggest look at this playlist by Deep Blue One Brown. It's very intuitive, and you should be able to get more idea of that. There are lectures from Stanford by Andrew Ng. It's also good. And if you want to read more about it, there is a book called Pattern Recognition and Machine Learning by Bishop. You should also look into it. So I added this reference, and we'll share this slide with you. So whatever reference you want to, whatever reference I added, you can look more into it. So any question? Okay, so that's it from mine.
Thank you, sir.
Thanks.
So we will concluding the Kaggle competition on Sunday. We right, Janmaji?
Yeah, tomorrow at midnight, submission deadline will happen.
Okay. It is not about competition, but it is like if you try, it will be good for you if you are interested in ML. So I am seeing 5 team now. Okay. Okay, then let's meet next Saturday.
Thank you.
Bye.
Okay. Bye. Thanks.
Thank you.